Hello, and welcome again to Microchip's Memory Technology Series. So what is I2C? Well, I2C is an acronym for Inter-Integrated Circuit. It can also be referred to as IIC or I2C. I2C was created by Philips, now NXP, back in 1982 as a simple serial bus for their various TTL integrated circuits or ICs. It provides a simple and robust serial communication between a peripheral device and a microcontroller. Today, about 40 years later, almost all microcontrollers sold by any supplier include at least one connection option for I2C communication. Why? Because I2C devices, compared to other protocols, are slightly lower costs to manufacture due to the lower number of logic gates needed to build the I2C interface. And it only takes 2 pins to implement, which also translates to low cost. And this lower cost has made I2C the most common and widely used serial bus across most applications, including IoT, consumer electronics, industrial equipment, automotive, and aerospace. Here's some details about the I2C protocol. I2C is a synchronous protocol that allows a master to initiate communication with a slave device. I2C protocol is a master-slave communication, with the master providing the clock, which effectively becomes the data transfer rate or clock frequency. It is a bidirectional bus, meaning the master can write to the slave and read from the slave. And it is a serial bus, which means data is clocked or shifted bit by bit. And there are 2 bus lines, serial clock, SCL, and serial data, SDA. In I2C, there are 5 speed categories, including standard mode, fast mode plus, high speed mode, and ultra fast mode. These speed categories range from 100 kHz to 5 MHz. 100 kHz up to 1 MHz are very similar, while 3.4 MHz requires some special considerations, and 5 MHz, being unidirectional, requires yet even more special attention. But by far, the most common I2C speed categories are standard mode, and fast mode plus, because these 3 are the easiest to implement. Here's an example of 4 devices connected to the same I2C bus. The microcontroller is the bus master, and the 3 slaves are a serial E2, a digital temp sensor, and a fan controller. R1 and R2 are the pull-up resistors, which are required for I2C devices to communicate properly. This is because I2C protocol works on the premise that the SCL and SDA bus lines are open drain or open collector. The transmitting device just lets go of the I2C bus to create a logic 1, and pulls or drives the line to ground to create a logic 0. Next, let's look at an I2C waveform. At first, the waveform might look a bit complex, but if we break the waveform down into sections, then it will become much easier to decode. All I2C transactions are initiated with a start condition. The start condition is defined as the master driving the SDA line low to a logic 0 while SCL remains high. And note that it must be initiated with the I2C bus in an idle state, meaning the SDA and SCL lines are both high, or a logic 1. The slave address immediately follows the start condition, and it can be 7 bits or 10 bits long, although the 7-bit slave address is by far the most common. The slave address will be specified in the device datasheet, and it is important to note that each device on the I2C bus needs a unique slave address. Next is the read and write, or R/W bit. It immediately follows the slave address, and together with the slave address, form the control byte. This bit informs the slave if the master wants to read or write. A 1 indicates the master wants to read from the slave, and a 0 means the master will write to the slave. This is easy to remember by just looking at the R/W symbol, as there's a bar over the W, meaning low is its active state. The next section is the acknowledge bits, and we can think of the acknowledge bit like a handshake between the master and the slave. They occur on every 9th clock cycle, regardless of where we're at in the I2C protocol. The device receiving the data is responsible for generating this acknowledge bit, and since I2C is bidirectional, this can either be the master or the slave. A 0 means the receiving device acknowledges or acts, and a 1 indicates the receiving device did not acknowledge or nacks. Coming from the slave, an ACK indicates the byte was received correctly. Coming from the master, an ACK requests that the slave transmit the next byte in the operation, while a NACK signals the end of the operation. Next is the data byte, and the data byte, or data bytes, contain the information being transferred between the master and the slave. The data contained in this byte can be command bits, register settings, memory contents, sensor readings, or any number of things. And the number of data bytes transmitted is determined by the operation being performed and the structure of the slave device being accessed. Common examples are the word address or register address that the master wants to access, the data to be written in a write operation, or the data from the slave requested in a read operation. And finally, the last section of the I2C protocol is the stop condition. All I2C transactions should be terminated with a stop condition. The stop condition is defined as the master releasing the SDA line while the SCL signal level is high. After a stop condition, the I2C bus will remain in an idle state and will be free for the next I2C transaction. Well, that is I2C. Here are some links to some other videos in our memory technology series. Since you just watched What is I2C, you may enjoy our What is SPI video since it builds off I2C to explain the differences between I2C and the faster SPI serial bus. Thanks for watching.